Bismillahirrahmanirrahim. Dear students, I'll start lecture number 1 of week number 11 and continue on with the concept of conditional expectation. If you recall from the last lecture, the conditional expectation of a random variable x given y is nothing but the expectation of random variable x for each value that y can take, and I told you that this conditional expectation can be a different number for a different value of this y. So we can effectively call the conditional expectation of x as a function of a random variable y. Expectation of x, the conditional expectation of x, can be called a function of random variable y. So you can write it as a function g of y. Function, a deterministic function of a random variable y. So if this is the case, we can call this expectation as a derived random variable. You know, function of a random variable is another random variable. Okay, so if that is the case, you can write it as, for example, u, which is again the expectation of x given y. So this is now important. Conditional expectation of a discrete random variable x given y is effectively a function of the random variable y, the conditioning random variable y. So I can call this function as a random variable. It is a derived random variable now, so I give it a name u. So now u is our new random variable. Just on an interesting note, let's try to calculate the expectation of this u. So you might be thinking, what will be the expectation of this derived random variable u? So there is a theorem in your textbook, and that says the random variable u, which is the expectation of x given y, has expected value e of u, that can be written now as the expectation of all this. You see, u is all this. The expectation of u is e of x given y. And so we can write it as, you just open this summation operator, so it will break up into three entities: the summation sign, the internal thing, the within the brackets, and then the PMF. So you can write it as summation on y, expectation of x given y is equal to y, and then you multiply it with the PMF of y. Now there will be a question that why we have written now the summation on y and we have multiplied it with the PMF of y, or the expectation multiplied with the PMF of y, because we see that u is a function of y. So, and by the way, this ultimately ends at some very simple expression. What is that simple expression? I'll tell you once I have proved that. So I'll move on to prove why this expectation of u can be written as a very, very simple expression. So let's see. Let me now prove that. Okay, let me give you first quickly. The simple expression is nothing but the expectation of x. So you see, the expectation of the conditional expectation of x given y simply turns out to be the expectation of x. But how? I'll show you through a proof. So I write expectation of x given y, and it is nothing but summation on y, expectation of x given y is equal to y times PMF of y but what is this expectation? Always remember, when you open up the expectation operator, three things emerge. The summation sign, the thing which is inside the brackets in the argument of the expectation, and the third thing is the probability distribution. So now if you open up this summation y will stay there, this piece of y will stay there, but how do you open this? This is the expectation of x given y. So you will have summation of x, summation on x, x times the conditional PMF of x given y. Okay. So we have now been able to write this as this. I hope this is very clear to you. But you know that I can always interchange the summation signs. So I write it as such: summation on x first, and then summation on y, and then x times p sub x given y of x given y times p sub y of y. Now move this x here, because this x should remain within the summation sign on x, but it can be taken out of summation on y, because this x is behaving as a constant when you take summation on y. So now I can write it as summation on x times summation on y, p sub x given y of x given y times p sub y of y. But if you recall, p sub x given y, we used to write it as p sub x comma y of x comma y divided by p sub y of y. This is the formula that we have already discussed many times. So now you see, you can write this as p sub x comma y of x comma y as p sub x given y of x given y times p sub y of y. This is x given y. So you see, all this can be written as this. So what we see here is all this is nothing but the giant distribution of x comma y. Okay, so now I can write it as summation on x times summation on y, and all this is nothing but p sub x comma y of x comma y, the giant distribution through our older formula. And you already know that when you sum the giant distribution on a variable, you get the distribution, the marginal distribution on another random variable. So just read this and you will see that this can be written as the PMF of x, because when you sum the giant distribution along y, you get the distribution on the other variable, which is now x. So all this can be written as p sub x. So I can write it as summation on x times, and all this is p sub x of x. But again, you see now, summation on x times p sub x can be written as the expectation of x, and this is exactly what I told you. So you see the importance of this theorem. When you have to find the expectation of a conditional expectation, you do not need to go into finding and calculating all these things, you simply can take the expectation of x, the expectation of the parent random variable x, and this will be exactly the same expectation as this. You know, theorems and formulas are useful in quickly moving through the numerical problems. So this is a quick look on one part, one angle of conditional expectation. I'll move on and discuss now another concept, and that is of independence of random variables. So my next topic is independent discrete random variables. You already know that when you have independent random variables, independent events, the probability of their joint occurrence, A intersection B, can be written as P of A times P of B. But now we have random variables, and you know that each random variable is represented, the probability of a random variable in totality is represented by its PMF. So this formula can be written in the form of the probability distribution in the form of PMFs. It can be written as P sub x comma y of x comma y, and that is equal to P sub x of x times P sub y of y. Remember, this is the basic formula to establish the independence of two random variables. But remember, this expression, this equation is represents the equality of functions, which means for each value of x and y, these two sides should balance. Similarly, we can also write P sub x given y of x given y, if it is equal to P sub x of x. This means the occurrence of y has not affected the probability of occurrence of x, and so x and y are independent. And we can also write P sub y given x of y given x as P sub y of y. So this is another way of establishing the independence of two random variables. This and this mean the same thing. You can always try to prove that at home. This means probability of occurrence of x given y has occurred does not affect the probability of occurrence of x. So when the unconditional PMF of x is equal to the conditional PMF of x, they are called independent. To establish the independence for small sample spaces, this formula can be very useful. Remember, this is functional equality, which means for each possible value of x and y, the product of their individual probabilities of these values should be equal to the probability of the joint occurrence of these two values. If this is the case, you can easily establish and verify the independence. Independence has a few advantages, but we'll in the course see how we can exploit those. First, I'll move on to give you a very quick example on how to establish the independence through this particular formula. So let me move on to the next slide, which is page 28, and I'll do an example. Suppose I have a giant distribution of x and y. Suppose there are two values of x, as is x is equal to -1 and x is equal to +1, and you have three values of y, which is say -1, 0 and 1, or call it +1, and then we have the giant distribution of these, and assume that the probabilities are distributed as such: 0, 0.25, 0.25, 0.25, 0.25 and 0. Suppose this is our sample space, and we need to check this. Or x and y independent, number 1, and number 2, or x and y uncorrelated. So let me first check the independence. So I'll provide the solution. For independence of the two random variables x and y, I need to establish that the giant occurrence of the two, the probability of giant occurrence of the two random variables is equal to the product of the individual occurrence probabilities. And from here you also know that the distribution of x and distribution of y can be written using our usual method. For x is equal to -1, the probability is 0.5. For x is equal to +1, again the probability is 0.5. For y is equal to -1, probability is 0.25. For y is equal to 0, it is 0.5, and for y is equal to +1, it is 0.25. So we have this p sub x available here, and we have this p sub y of y, the marginal distributions of x and y available here. So now we need to check. Take, for example, one value of x, one value of y, and find their individual probabilities, and then do the product, and use the same values of x and y and see if the probability of the giant occurrence of the two is equal to this product. If this is the case, move on to the next possibilities of x and y, and so on. If all such products are equal to the individual to the corresponding giant occurrences, then you will have established the independence. So, for example, I take x is equal to -1 and y is equal to -1, the first entry. So p sub x of -1, you know, is 0.5. P sub y of -1 is 0.25. P sub x of -1 is 0.5. P sub y of -1 is 0.25. So what is their product? P sub x of -1 times P sub y of -1. So it should be 0.5 into 0.25, some number. But what about P sub x comma y of the same values of x and y, which means -1 comma -1. So P sub x comma y of -1 comma -1 is here. X is equal to -1, y is equal to -1. So this is equal to 0, which is obviously not equal to the value here. So even on the first check, we have found that x and y are not independent because this formula doesn't hold. So we write, don't need to check the other possibilities, simply write that x and y, or not independent. Dear students, I have solved this part, explained this part, but you need to take this part, the second part, as homework. You need to see, you need to check if x and y are uncorrelated. If you recall, I had given you some pointers on covariance and correlation. If you recall, covariance of x and y is the product of is the expectation of the product minus the product of the individual expectations. And covariance is equal to 0 would mean that the two random variables are uncorrelated. But please do solve this as your homework. As a quick information on what are the advantages, what are some of the advantages of independence, let me summarize this through a theorem that is already given in your textbook. We'll see what we mean with this. For independent random variables x and y, first, the correlation of x and y, which is nothing but the expectation of the product, that can be written as the product of the individual expectations. You can always try to verify this. You can always try to prove this. But you see, if x and y are independent, the correlation can be simply written as the product of the expectations. So to find the correlation, you do not need to utilize the giant distribution of x and y. You can simply use the individual marginal distribution of x, marginal distribution of y, and then find the corresponding expectations, and that will give you the correlation between the two. But this is true for the case of independent random variables. So you see, when random variables are independent, it simplifies our mathematical analysis. In B, the expectation of x given y is equal to y is now nothing but the expectation of x, because we see that if x and y are independent, the occurrence of y does not affect the probability of occurrence of x. So if it does not affect the probability of occurrence of x, then the conditional expectation and the unconditional expectation should be the same. Similar is the case when we simply swap them. Y given x is equal to x, this should give you the expectation of y. And we have in chapter number 1 already discussed that if x is independent of y, then y is also independent of x. And we now move on to the variance of the sum. If you recall, it was the formula was variance of x plus variance of y and then the covariance term. But if x and y are independent, you do not need that particular term. Please do prove this at home. This will give you more insight into the formula. So, but if we accept that this is true, and obviously it is true, the variance of x plus y is nothing but variance of x plus variance of y. To find the variance of x, you simply need the expectation and PMF of x. To find the variance of y, you need expectation and distribution of y, and you then simply add them up. You will simply need one-dimensional distribution. But if you are not sure whether x and y are independent, or if they are not independent, then you have to utilize this this giant distribution formula. And the last part is covariance of x comma y for independent random variables is always equal to 0. Okay, so we have discussed, in fact repeated some information about some points about the independence of two random variables. Let me quickly repeat these. So a quick review. Independence of two random variables. The independence of two events can be written as such, which we discussed in chapter number 1. When we convert this formula to random variable, which means multiple events put together in a collective form, in the form of distribution. So the same formula turns out to be like this. The probability of giant occurrence should be equal to the probability of individual occurrence, and this means the same. We then solved an example where we had a giant distribution and we found the marginal distributions of x and y, and we needed to check if x and y are independent, and then we also needed to check if x and y are uncorrelated. I left this part as your homework, and I solved this part of the problem. So you see, you need to basically verify this formula for all the possibilities of x and y. The equation should hold. So for example, you take x is equal to -1 and y is equal to 1, the first entry. The individual x is equal to -1 and y is equal to -1 probabilities are 0.5 and 0.25 respectively. But what about the product? It is p sub x of -1 times p sub y of -1, which is this part of the formula, and this will give you 0.5 into 2.25, which is some number, some non-zero number. Then you have to come to the left side of the formula, which means you will use the same values of x and y, which is -1 and -1, and check the probability of giant occurrence of these two values, which means p sub x comma y of -1 comma -1. So p sub x comma y of -1 comma -1 is 0 here, and so this is not equal to this probability, and so this formula doesn't the two sides of this formula do not balance, and so you do not need to move on to calculate the other possibilities and other possibilities of this formula. Just claim that x and y are not independent. Then we gave a quick hint on why is independence important, and this is established through briefly established through this theorem. If x and y are independent, the correlation between the two can be written as the product of individual expectations. You need to prove this. This is very, very simple. Please do this at home. This is obvious. The expectation of x given y, if x is independent of y, should be equal to simply the expectation of x, which means the occurrence of y does not affect the probability of occurrence of x and correspondingly the expectation of x. Same is the case with y, and we already know that if x is equal to if x is independent of y, then y is independent of x. So if you know this formula, this part C is automatic. But the variance of x plus y, if you remember, if the variance had three entities in the formula, variance of x plus variance of y plus 2 times covariance of x and y, but when x and y are independent, this covariance term vanishes and you simply are left with these two individual variances, which is much simpler and easy to calculate. And the last part is if x and y are independent, their covariance goes to 0. Now, my dear students, I'll move on to kind of generalize my formulas for two-dimensional distributions to n-dimensional distributions. So my next topic and the last topic for today's lectures is more than two discrete random variables. Which means how to write the distributions of more than two discrete random variables. So first we'll see what we mean by giant n random variables taken together, which means giant PMF of n random variables x1, x2 till say xn. The giant PMF of random variable of n random variables x1 till xn can be written as P sub x1, x2 till xn of x1, x2 till xn, and this is nothing but the probability that x1 assumes this particular value, random variable x2 assumes this particular value, and so on. Random variable xn assumes this particular value. So you see, this means the giant PMF of n random variable means random variable x assumes this value, random variable x2 assumes this value, and so on. Random variable xn assumes this value. So now, from now on, we'll write the giant distributions of 3, 4, 5 random variables taken together as such. Now, consider an experiment with 4 random variables, just as an example. So, how to find marginal distributions of some variables from a giant distributions of some random variables. So, suppose your giant distribution is on 4 random variables w, x, y, and z, and you need to find a marginal distribution on x, y, and z, which means you have a 4-dimensional distribution, and so it can generate many 1-dimensional, 2-dimensional, and 3-dimensional marginal distributions. So, for example, you need to find the marginal distribution of x, y, z, the 3-dimensional marginal distribution, using this parent 4-dimensional distribution. So, if you recall the formula, I told you that when you have a giant distribution, to find the marginal distribution of a random variable, you sum the giant distribution on all the variables except the one for which you want the distribution, for which you want the marginal distribution. So now you want the marginal distribution on x, y, and z. So you need to sum the giant distribution on the variable missing here. The variable missing here is w. So now if you sum the giant distribution, 4-dimensional distribution of w, x, y, z on w, you will get the marginal distribution on x, y, and z. And so, for example, you want to find the marginal distribution on w, z of w, z from this giant distribution on 4 random variables w, x, y, and z, w, x, y, and z. you will simply sum the giant distribution along the variables which are missing here. The variables missing here are x and y. So you sum along x and then you sum along y the giant distribution, and you will get the marginal distribution on w and z. Just as another example, suppose you want to find the marginal distribution of x only by utilizing the giant distribution of w, x, y and z. So you sum along the missing variable here. So you see here the missing variables are w, y and z. So summation on w, summation on y and summation on z applied on this giant distribution will give you marginal distribution. So you see the formulas for two-dimensional distribution are easily generalized to more than two random variables, even 3, 4, 5 and so on. Now my dear students, we'll see how we can extend the concept of independence to n random variables. We have been able to write the giant distribution of random variables. We have been able to see how we can find the marginal distributions. So now, what about the independence of n random variable? So we write that the discrete random variables x1, x2 till xn are independent if and only if the probability of their giant occurrence is equal to the product of the individual occurrence probabilities, which means the probability of giant occurrence, which is x1, x2 till xn of x1, x2 till xn is equal to the product of the individual occurrence probabilities, which means p sub x1 of x1 times p sub x2 of x2 times so on p sub xn of xn. So this is what we mean by the independence of n random variables. If you recall, just recently we discussed the concept of independence of two random variables where we had, say, x and y. So this formula is basically a generalization of the same formula. If similarly, we can write the expectations and variances, in fact covariances of more than one random variable, but you need to just refer to the book and you will see how you can write this. If n random variables are independent, if n discrete random variables are independent, their expectation can be written as the product of the individual expectation of each random variable. So please go to the book, refer to the book, and you will find some formulas there. It is easy to grab. We will not spend much time on this. I'll just quickly summarize now some important formulas that we have discussed in this particular chapter. So last part of today's lecture, some important formulas. Number 1, expectation of ax plus b is equal to a times expectation of x plus b. We have thoroughly discussed this in the initial part of this chapter. Second, expectation of ax plus b y is simply A times expectation of x plus B times expectation of y. You know, sum of expectations the expectation of the sum of two random variables is always equal to the sum of individual expectations of those two random variables, no matter if they are independent or not. Thirdly, the expectation of the product can be written as the product of the individual expectations if and only if x and y are independent. So expectation of the product can be written as the product of individual expectations if x and y are independent. Fourth one, just a quick recall, variance of ax plus b is a square variance of x. You know that shifting does not affect the variance of a random variable. I gave you a good lecture time on this concept. Fifth one, variance of ax plus by. Now two random variables are involved. Variance of ax plus by is a square variance of x plus b square variance of y plus 2ab times covariance of x and y. And then the last one is variance of x plus y is equal to variance of x plus variance of y if x and y are independent. You see, if x and y are independent, this covariance term simply vanishes. I have given you a small homework around this, so please do solve this homework. A quick look on what we have learned about multiple discrete random variables. So if we have to analyze more than two random variables, first you need their giant distributions. So you see, and remember this concept of two random variables taken together, that is easily extendable to more than two random variables. For example, n random variable, you simply write the distribution as this. And if you want to find the marginal distribution of some random variables from the parent multiple random variable distribution, for example 4 random variable w, x, y and z, you can find the marginal distributions of one or more than one random variables out of this parent giant distribution by summing up the giant distribution on all the variables except those on which you want the marginal distribution. For example, if you want the marginal distribution on x, y and z, the giant distribution on x, y, z from this 4-dimensional distribution, you sum this 4-dimensional distribution on a random variable which is not here. Obviously w is not here, so you sum it along w. If you want the giant distribution on w and z, you sum the 4-dimensional distribution on the variables which are missing here, and the variables missing here are x and y. And similarly, for the probability distribution of x, if you sum the giant distribution, 4-dimensional distribution on w, y and z, you will obtain the PMF of x. The concept of independence of n discrete random variables is also automatic, as was the case for two-dimensional distributions for two random variables. So for n random variables, the formula easily can be generalized. So probability of the joint occurrence has to be equal to the product of the individual occurrence probabilities. Then we reviewed some of the very important formulas for this particular chapter. The expectation of ax plus b is simply a times expectation of x plus b. If you have two random variables, the formula takes this shape. The correlation is equal to the product of the individual expectations if x and y are independent. Variance is already known to you. If you want to find the variance of the sum, it extends to this. But if x and y are independent, then this variance of x plus y stays the same, like this. This part simply vanishes if x and y are independent. Thank you very much, my dear students. Zever will give you, Mr. Zever, my colleague, will give you, and the other instructor of this course will give you some assignment from this chapter, and you have to, and will give you some time to solve that assignment and submit that assignment. So please be attentive to that as well in the interactive session, and keep on checking your emails as well. Thank you very much.